Just tell me, when to. Yeah. So, hello everyone, and welcome to PyData Delhi Meetup number 40. And it's been so. This is our third meetup since our lockdown started, and this is the third version of the online meetup that we're doing. So yeah, we have amazing speakers today, and so I'm just gonna start with introductions first. So welcome everyone, and to PyData Delhi meetup. And yeah, so just a little background about what PyData Delhi is and what we are. So I'm sure, most of you have used open data source tools like Pandas, NumPy, Scikit-learn, and Matplotlib and all. So all these tools are open data source tools, and they are basically maintained by developers and contributors all around the world. And so they don't have a definite source of income and support to sustain for a long period of time. So that's where a non-profit, which is known as NumFOCUS, steps in, and they basically helps for the sustainability of the projects which comes under NumFOCUS umbrella. They provide them funding, contributors, developers, sprints, and everything which is necessary to be maintained for the projects for the long period of time. And PyData Delhi is actually PyData is an educational initiative by NumFOCUS to promote the education and the awareness about data science all around the globe. And it has several chapters all around the world. And PyData Delhi is like the fourth largest chapter all around the world. And we started back in 2016, and since then, like, we've been growing exponentially. And as you can see, this is the 40th meetup we are doing. And yeah, and we have done 3 conferences so far. The conference is just like an annual attempt for us to show our work. But yeah, sadly, we are not having conference this year due to COVID and all. But yeah, I mean, I do have some exciting news on that in upcoming slides. So yeah, please sit tight. And yeah, so that's about like NumFOCUS and PyData. And yeah, so moving on to next slide. Yeah, so as we know that NumFOCUS is entirely dependent on, it's a non-profit, so it's entirely dependent on the donations that are being provided by the big companies, corporates, and everyone. But it's not like the only corporate big companies and startups are responsible for the donations. You can also make a difference. You can just head over to these links and uh, donate whatever amount you feel like. Every penny helps, and I'm sure that your donation would help us steer us through this crazy times that we are in. Yeah. So yeah, the meetup is live on YouTube, and I'm sure like the people who are watching, that. And yeah, you can head over to our PyData YouTube, and there would you would be you can see that we are going live, and this is the link that you can go over, and just you will be redirected to a live stream. So we have 2 speakers today. So I'm just going to do a small introduction, and yeah. So we have Hariram Gopal from Nagaro. He has 7 years of experience in data science and analytics, and he has been working on exciting problems and solving them as you go. And yeah, he would be speaking on reinventing inventory planning through reinforcement learning. So more of that in a minute. And yeah, another speaker for today is Dr. Deepak Pathak. He is assistant prof at Carnegie and also a researcher at Facebook AI. And he has worked at number of different research areas like computer vision, machine learning, robotics, and self-supervision and all. And he would be speaking on self-supervision, curiosity, and modularity for building robots that would generalize. So yeah, more of that in a minute. Yeah, where to ask questions. So we are live on YouTube, so you can definitely put your questions in the YouTube chat, and we have moderators that would be going through the live chat. And after the talk, we would be shooting our questions to the speakers, and they would be answering on rolling basis. So yeah, feel free to add questions, and please don't spam the YouTube chat, because that's not something that is nice. Okay. Yeah. So code of conduct. Yeah. So we have a code of conduct for every physical meetup, or I would say the annual conference or any physical event that we are having. But the thing is, like, we make sure that the code of conduct is also being applied in an online setup that's we are having right now. So just a small thing, like, the code of conduct is simply something that you have to be nice, and don't do something that would hurt the sentiments, or make anyone feel uncomfortable. If you have time, you can also refer to our full code of conduct, which is on the link below that is being showed on your screen. So yeah, if you want to give a talk, so we have a GitHub repo which has basically all the issues, on which if you want to propose a talk, you can just head over and create an issue over there. There are a bunch of required fields which we need to input over there, and after that we'll take the issue from over there. We get it reviewed. We'll see if it is missing something, or if there's something need to be edited. And after the talk is accepted, you can just deliver it in our online format. That's like we're having right now. So the link is this, you can see on your screens. Where to find us? So we are everywhere. Like, we have worked hard on our social media or marketing side, and we are omnipresent. As you can see, we are on the all of the major social media platforms, as you can see. So yeah, please just go over there, follow us, and yeah, you can also see a Illuminati sign that is bomb banging in the between. Yeah. Future meetup. So okay, so we also have our public Google Calendar, which is something like, if you subscribe to this calendar, you will automatically get notified for our future meetups, or our community calls, or our quizzes, or our, what do you say, anything that we are doing for the PyData Delhi. And we create a public event over there, so you can check out, you can check your Google Calendar. If you are subscribed to that, subscribe to our Google Calendar, and it will pop up in notifications that we are having a meetup and all. And yeah, this is the link that you can see on your screen. You can just head over to this link, and subscribe to the Google Calendar. Yeah, okay. So initially I was, mentioning about that we are not having conference this year, like our annual conference due to COVID and all. But yeah, we have some exciting news on that scenario, which is something like, all the PyData chapters from around the globe. There are, I think, 180 plus chapters all over the world, if I'm sure. I don't remember the exact count, but something around that. They have joined their forces together to deliver a global online conference for attendees across the globe. So if you just go over to this link, you can see that the conference is, like, we are preparing for the conference, and the CFP is basically call for proposals is live right now. It is open until 2nd of August, which is the first round of acceptance for CFP. The extended deadline is 16th of August, but that is the second round of submissions. So if you just head over to this link, and you'll see the CFP page, you can submit your proposals over there. And like, the whole PyData Delhi team is working hard in collaboration with all the chapters around the globe to deliver this conference and make it as interactive and as good as the physical one. So yeah, it's just a conference which will be having talks, sprints, poster sessions, mentored sprints, and a lot of things. And we are also having like a digital hallway track to make sure that you can interact with or network with the attendees as you do in a physical meetup. So yeah, a lot of interesting things are happening in the PyData space. So yeah, do watch out for this link. And if you have any queries, you can mail us at delhi@pydata.org. This is our official email. And if you think like your company would be interested in sponsoring this conference, yeah, please feel free to sponsor us. You can find all the relevant links and the sponsorship prospectus on the website, which is I think somewhere in the channel, on the website. And if you have any queries, you can definitely mail us. And yeah, it's working great. And like, we have time, like, we are doing it in November 11th to 15th, but yeah, it's going to be great, and we are so excited for that. We already have so many proposals from all around the globe and from India also, which is a very interesting thing to see. I must say, and yeah. So let's move on to next slide, which is, yeah, let's get started. Like enough of an introduction and all. So yeah, let's move on to the. Okay, so one more thing, like I totally forgot this every time when I give a introduction and all. My name is Sanket Verma, and I organize PyData Delhi with all of these beautiful volunteers who are on the call with me right now. And I've been doing this volunteering for the past 3 years, and yeah, we do stuff and make community come together and help that and make sure that everyone have as fun as make sure that everyone have fun as much as we have during the organizing the events and all. So yeah, that's enough about me. And so yeah, let's get it started. So Hariram, yeah, over to you, and you can just start your screen share.
Thank you, Sanket. Thank you for the introduction. Thank
Yeah.
you for arranging this. Thank you, PyData team, on the volunteers. So
Yep.
let
So
me share my screen. Yeah,
yeah, sure. Yeah, I can see. So yeah, awesome.
great. So let's get started. So good
So
morning, good afternoon, or good
yeah,
evening. So
so Hariram, yeah, please just give a small introduction about you, because it will be good that it will come from you.
absolutely, yeah. So myself, Hariram. I work for Nagaro. Nagaro is a software services and IT consulting company, which has been operating in this area for more than 30 years now. So we are 6,000 plus employees, and we are present in 22 countries. Uh, in data science and big data and analytics, we have 100 plus employees who are dedicatedly working in this space. So proud to be in Nagaro. But before Nagaro, I worked in healthcare domain with Novartis. I also work for Essilor, which is the leading spectacle manufacturing company. So this is about me. I have overall around 7 years of experience in data science and analytics. Um, so with me, I have Rishabh and Vijay, who are my colleagues, who also worked on and contributed on this project. If you are there, maybe you can give a shout out, Vijay and Rishabh.
Yeah, hi everyone. Rishabh this side. I'm working in Nagaro as a data scientist, and it's been around 1 year since I joined Nagaro, and I'm having 1.5 year of experience in data science. And thank you.
Yeah, welcome Rishabh to the PyData.
Yeah, thank you.
Yeah, thank you, Rishabh. So apart from data science and work and all that stuff, I'm a huge fan of football. I play table tennis regularly, not in COVID times, before COVID times, yeah. And ardent fan of chess from childhood. So this leads to the our topic, which is reinforcement learning and inventory planning. So one of the things that really I mean. Intrigued me with reinforcement learning. Maybe I started my reinforcement journey that time is because of AlphaZero, which is a chess engine which bet the strongest chess engines available. So as a chess fan from childhood, so I was so intrigued, and what is reinforcement learning? I want to learn this, and I was fortunate enough to learn it and apply it some of the business problems. So that's one of the business problems is what I'm going to talk about today. So let's briefly go over the agenda for today. So the agenda would be a gentle, very high level introduction to reinforcement learning. So those who are already really familiar with reinforcement learning, please be forgiving and bear with me for a few slides. Just many of the data scientists are not familiar with this paradigm, so I'm going to give a really high level introduction with some pictorial slides to send across the message. Then I'm also gonna give a similar introduction, maybe a shorter introduction to inventory management, which is this inventory management domain, how it has been traditionally done, what are the challenges, and so on. And then we are going to marry this reinforcement learning and inventory management through this reinforcement learning approach, and how and why it's a good fit for this problem. Finally, we are going to end off with a dashboard kind of a demo which showcase the output of reinforcement learning for inventory management, right? So let's move on to the first agenda, which is introduction to reinforcement learning. Right. Many of us would have seen this picture if we had read Sutton and Bartow. So it's really, really fascinating how reinforcement learning is so close to real life learning. This is a gazelle which was born just 30 minutes ago, and it is able to run at such a quick speed. It has learned through trial and error. So trial and error is a great way of learning. So it is seen in our evolution. It's seen with our learning process. So it's a great way for computers to also learn. So earlier I was talking about chess. So AlphaZero, which is one of the strongest chess engines that has been built through purely through reinforcement learning. It learned chess for just 4 hours, and it could beat everyone in the planet and also every engine on the planet. So that's so incredible and intriguing. So our ex-world champion Viswanathan said jokingly that we have been playing this game for over 600 years, and all it takes for the engine is just 4 hours. That's really humbling, and we can see the effect of reinforcement learning. We can see reinforcement learning conquer other areas, such as it can play poker, which is generally associated with human skills, like mind reading skills and so on, right? And it can play complex games such as Dota, and it is also used in robotics. So it is able to find novel ways to a problem that we have been already solving for centuries. So it's a great way to learn for machines. So this is the build up for reinforcement learning. Of course, reinforcement learning can be used beyond gaming, robotics, and it can be used in real life too. So let's just quickly see, what is this paradigm of reinforcement learning. So reinforcement learning is mostly used in places where there's a sequential decision making, right? So not in a sort of a IID data that you have with supervised learning. So in supervised learning, we all know it works on training data. So when you give a bunch of images, this acts as a supervisor, and it learns to say this is X kind of image. Let's say this is a cat and this is a dog, through learning and back propagation and so on. In unsupervised learning, we do not label the data. We give the data to the model, and it is able to find the inherent characteristics and group them into separate uh, homogeneous groups. But in reinforcement learning, it's sort of different, where we tell an agent to do something or choose something from a set of things or do an action. If it does good action, you give a reward. If it doesn't do a good action, then you give a penalty. So it's as simple as real life learning. So that's the different paradigm of machine learning that reinforcement learning brings through. So what are the key elements of reinforcement learning? So whenever anyone starts a new topic, it's good to start with the very basics and very basic example, and then scale it up to bigger examples. So that's exactly what I'm going to do. I'm going to start with tic-tac-toe, a game that has been played by all of us during some point of time, during childhood, during boring lectures, during boring webinars like this, probably, right? So in tic-tac-toe, let's say, we'll see, how reinforcement learning will approach tic-tac-toe and what are the key terms and key elements of reinforcement learning. First, there is an environment. Environment is the tic-tac-go game itself and its rules, right? Then there's the agent, which is going to play and learn through trial and error. Then there's the state. State is a position of a game, is called state. Then there's action space. Action space is nothing but X or O, right? And where you want to place this X or O based on what player you are. Then there is an important point of a reward. Reward is what is given to an agent, which helps it learn. For example, reward could be a 1 if it wins, it could be a -1 if it loses, 0 if it's a draw. So this is very important thing for the agent to learn or change its approach. The approach, what we are talking about, the policy is the set of decisions that the agent makes in order to win a game. So we have to, in order to train an agent, we have to play this game over and over again, hundreds and thousands of times, and therefore episode is playing the game one time is called an episode. And finally, we have a value. Value can be associated with any state that you're in or any action you take, right? So the value is how good or bad it is. Right? For example, if I am X player, this would be a bad state for me, right? It would have a bad value. So typically in reinforcement learning, you would see this kind of a diagram where an agent interacts with the environment through its actions, and environment gives its output in the form of a reward and the next state. So agent does not know entire environment. It can only interact with the environment through its action. It does not know all the rules, but it tries and figures out through trial and error. So that's the brief introduction to the terminology. Then we come to the key point of expected returns. So in previous slide, we talked about the rewards. So I'm loosely using rewards and returns are the same. So returns are something, like if I invest 10 rupees in today, I'll get 11 rupees tomorrow. So that's the return I'm going to get. So similar to finance, even in games or any other problem, we can quantify the returns that you're going to get. But how would you calculate these returns? So the returns will be infinity if if the if the task is very continuous. For example, inventory management can be a continuous task. Your company will run in perpetuity, so the rewards would be infinite. So in order to be mathematically more convenient, we discount the future rewards. We say the future rewards are not certain, therefore we discount the future rewards by a discount factor, that is gamma. So the agent learns, says that the immediate reward, it gives the highest value. The rewards that going to come in future, it's going to discount it by a factor of, let's say, gamma, which lies between 0 and 1, most probably 0.99. Therefore, it even for a continuous task, we can find out what the reward is and we can train our agent accordingly. Then we always are talking about trial and error. So what is trial and error, right? So I try something and it doesn't, it's not a good action that the agent did, right? But maybe this time it was not good, but down the line it is good for me. So there should be always some exploration and exploitation trade-off in reinforcement learning. For example, if I say like I like some type of food, let's say Indian, Chinese, but I have not tried Thai food, so I will go and explore it. So if I like it, I will add it to my you know menu, or I will try it often. But if I do not like it, then I will discard it. So that's the trial and error in real life. Similar to it, we can program the agent to do this trial and error, explore the environment more and more, and exploit the part of the environment from which it gets the maximum gains. Next, we will talk about a little bit on the taxonomy of RL. So what are the different types of RL methods out there and how it works on a very, very high level. And I encourage every one of you to, if you can, put your questions out there in the chat. And if I'm going too fast and too slow, please let me know. So we can summarize the taxonomy of reinforcement learning, using this slide. There are, if you look at this table, there are model-based reinforcement learning or model-free reinforcement learning. There is value-based reinforcement learning, policy-based reinforcement learning, and on-policy learning and off-policy learning. This is what we are exactly going to talk about in the next 3 slides, on a very high level through pictorially. So I personally feel pictures we remember very well, and to understand the concepts, to drive these concepts, it might be too much to understand at one go. Therefore we'll see some picture. Through this picture we'll identify some intuitions out of it, and these pictures are of course borrowed from the very well-known sources too. Yeah. First, let's talk about policy-based methods and value-based methods. So in order for a reinforcement learning agent to learn, it can learn two things. It can learn the value or the value of being in a particular state or taking an action. So I always want to take an action that has a maximum value. So if we store all the values, if we store all the combination of state and actions, then I would know which action to take based on this huge matrix of state action value pairs. That is value based reinforcement learning. Policy based is where I do not want to know about the value. Okay, I will need the value, but once I know the value, I will calculate my policy. What should be my policy? Policy is my action. Then I will remember only my policy. I don't need those values. This is very well demonstrated in this example, which is given by David Silver. So if you see this maze as a human, it's very, very easy for us to understand what's the shortest path for to attain the goal. I go here, I go here, I go down and achieve my goal in the shortest path. For machine, it's not so simple, especially in reinforcement learning setting. It's not very sample efficient. So after it learns through thousands of iterations, either it learns the value or the policy. So here in value, you see for each of this state in which it is in, it has given some value. For example, the starting state is minus 16, which means I'm 16 steps away from the goal. Then it's minus 15, which is 15 steps away from the goal. So I will always want to go to a state which has a higher value. So that's how my path is defined. So this would be my path to my goal. Contrast to policy based, it does not remember all these values. It just remembers what to do at a particular point. So if I am in this state, I move right. If I'm in this state, I move up, and so on. So it's pretty simple. But both has its pros and cons. Like every other algorithm, every other method, each algorithm has its pros and cons. But the state of the art techniques combine these two methods, policy based and value based methods, and these are typically called actor critique methods, which are used to solve real life reinforcement learning problems. Then the another taxonomy we are classified into model based approach and model free approach. Model free approach are more common, model based approach are less common, but we'll just talk briefly on what is it. Okay, let's take a problem statement, right? Let's say on Friday evening, we need to go from office to home. So which path should I choose? Should I choose the freeway or not? Should I take, what all routes should I take to reach the home? Let's say there are multiple routes to take, right? So what I could do is, what a model based agent would do, it would already through experience of interacting with the environment, it has made a mental map, or it has recreated the environment by interacting with the environment. It has made this mental map. It's sort of like the agent is dreaming, right? So it knows, okay, at this time the traffic should be this and that, so therefore I will not take the freeway. So it decides based on the model of the environment itself. Whereas a model free approach, we do not know the environment, but we learn only through trial and error. Okay, previous 5 Fridays I took the freeway and I got stuck in traffic. Now I will not take the freeway. So this is model free approach. Again, each has its pros and cons, but the interesting thing here is, it is said that human brain employs both of these approach to make decision making strategies. This is explained by in the paper that is sourced here. The third and the final taxonomy, the reinforcement learning, is the on-policy learning and off-policy learning. So it's just a learning method of reinforcement learning. So either the reinforcement learning interacts with the agents through its action and directly learns from the environment, rewards from the environment. That is on-policy learning. Most policy gradient methods are on-policy. And there's off-policy learning. That means I interact with the environment, so I get some experience from that. I store this experience in the form of a replay buffer. So I train my reinforcement learning on this replay buffer, which is sort of offline data. So whatever I'm going to train here, whatever actions I'm going to take on this replay buffer will not affect the environment. So there are two types of learning methods also there. So any algorithm that you see out there, let's say from algorithms of deep Q learning, SARSA, and so on, will fall into either of these categories or multiple of these categories. But these three are the broad taxonomy of reinforcement learning. Right. So enough jargons and things about reinforcement learning. Let's see its applications. We want to use it in real life. So that's where the application lies, right? So when do you use reinforcement learning? We are so much used to supervised learning and unsupervised learning and recommendation engines and so on. But when what business problem do I encounter? Should I use reinforcement learning? Is it only games or beyond? No, it's not. the fortunate answer for us is used in multiple industrial applications where there is a sequential decision making. So it used in multiple optimization problems. A typical thumb rule which we are suggesting here is to use reinforcement learning when the problem is really hard to solve. There are a lot of decisions to be taken, and there are a lot of variables which affect this decision, and there's a sequential decision making process, and you have to optimize these things. So, and those sort of places, and you need a faster solution too, right? So that time you can use reinforcement learning. So if you need a slower solution, but the problem is really hard to solve, we can use genetic algorithms or advanced heuristic algorithms. If the problem is really relatively easy to solve, and it's need a slow solution, slow answer, it's not something very real time, and the latency can be very high, then you can use a mathematical problem solving way too. This is a thumb rule. I mean, it can be challenged, of course. So some of the industrial applications it's definitely in gaming, in robotics, in financial trade markets, in electricity trade. Interestingly, it is used. Traffic signal control. There are various papers published on this, and job scheduling is another. Job scheduling and employee scheduling, reinforcement learning are used extensively in various optimization problems such as combinatorial optimization problems and other problems. And the problem that on focus is inventory management today is also uses a reinforcement learning based approach. Let me take a quick pause here. Maybe give some seconds to digest this, and I can ask the moderators to see if there are any questions. Or
Yeah, we have a question, but I think like, would you like to take them right now, or would you want to take them after the talk?
yeah, absolutely, I can take it now.
Okay, cool. So the question is something like, the question is by Harshita, and the question is, can you please discuss the difference between the dataset collection and modeling techniques for model-based and model-free approaches in reinforcement learning?
Okay.
Yeah. Do you want me to repeat, or is it?
Yeah, I think it's clear. So
Cool.
I'm not going to go too much into it. I would encourage to explore this, but the basic, the environment is going to remain the same for both the approaches. For model free, the approach is different. What you're training is different. So model free, we are going to train to learn it to perform some actions, or to perform some actions that give you the best rewards, right? Without learning about the environment itself. Model based is an approach where you train it to know the environment itself. It's gonna remap the environment based on the experiences. That's the basic differences, and it will also reflect in the kind of data you're going to collect, kind of interactions, kind of learning that you're going to make, and so on. So
Yeah. All right. Thank you for the answer.
sure. Okay, so let's dive into the next rabbit hole of inventory management. It is a huge topic, and it's personally close to me also. I have been working in supply chain for around 3 to 4 years of my career. So I was lucky enough to marry this uh, data science and supply chain together to give this solution of inventory management using RL. So before going to RL, we will see the traditional approach that has been done, and the formula-based approaches, and few of its shortcomings. Because inventory management problem is not a new problem; it has been there for decades, and if not for centuries, right? Uh, People are handling this problem. So right. So I'm going to oversimplify this. We can talk about inventory for an hour. So since this is a lightning talk, I'm going to oversimplify it and say inventory management is having the right amount of stock at the right place, at the right time, at the right cost. So I'm going to simplify this using this decision. So we are going to say we want to have the right amount of stock to serve your customers in the right locations. Maybe you have hundreds of locations, right? And hundreds of products. At this complexity, you need to have the right amount for each of your stock keeping unit, and you have to order it on the right time, and you have to check the demand of each of this product. So it's a really cumbersome process, and it's a complex process in itself. But underlying thing, we can see two opposing forces in inventory management. If I want to have very high service levels, then I would say, okay, let me stock up my inventory. Let me have high amount of inventory, right? Let's take a grocery example. So if you want to stock bread in your grocery store, and there are 10 people buying bread from your store every day, 10 to 20 people, let's say. So I keep 30 pieces of bread, slacks of bread, right? So but that is surplus inventory that I do not want. So I'm locking up my working capital over there, and I'm losing some money. I'm incurring some holding cost. The bread can go stale, right? The product can be damaged, and I'm also losing that shelf space for some other products also. So I do not want to carry excess amount of inventory in order to increase my service levels. But what if I go in the other end of the spectrum and say I will keep only 10 slacks of bread, and because minimum amount of people that come to my place is 10, then I do not have any buffer. So if the 11th person comes in, I am not able to get that sale. Probably I would have had a margin if I were able to sell it. So I lose that opportunity, and definitely next time the person turning up to your store is going to be less. It affects your brand value, it affects your service level. So it depends upon the product also, to say, can I keep excess amount of inventory? Can I keep optimum or very lean inventory? One interesting example I can give is, let's say, medicine, right? So for medicine, the stocking strategy will be different. For example, I would go ahead and keep surplus amount of inventory for medicines. Even why? Because the risk of shortage of inventory is very high, because it could be a life, right? So it depends upon the product, it depends upon the price of the product. What is your inventory strategy? It's a difficult decision to make, what amount of inventory that you have to have at your store or your warehouse or any part of the supply chain. On top of this, adding to the complexities, there are various uncertainties in business environment. From your supplier side, let's say there's a bread supplier that is sitting 100 kilometers from you, and he says, I will deliver your product in 3 days, but it takes 4 days to deliver it. So there is some uncertainty over there. And as a company, you have to manage all your products. There can be product damage, products that can be stolen, and so on and so forth. So you have to cater buffer for all of these things. And from the customer side also, let's say, because of customer side, when I say customer, it's the market side. Suddenly there can be demand rise because of some situation. There can be demand fall, because forecasting of demand will always comes with some uncertainty. So we have to consider all these things you know while managing inventory, especially when we are managing inventory for thousands and thousands of SKUs at 10 to 50 different locations. It becomes a really complex decision making process of what to order and how much to order and when to order. To solve this, people have resorted to formulas, right? So to make these key decisions, right? So first thing is the safety stock. Safety stock is something that is calculated to say, at any given point of time, I need to hold this much amount of buffer inventory, right? So that's my buffer to cater to my uncertainties, but whether it's from the market, the customer, or from the supplier. So that is my safety stock to cater to uncertainties, right? Then they also have calculated a good formula for reorder point for the product, which says at what point should I order. Okay, so I have, let's say, 10 amount of bread today, and it is being consumed on a daily basis. So at what point should I order when I have 5 packets of bread, or should I order when I have 3 pieces of bread? So what is the right time to order? This depends upon my lead time of order, this depends upon the type of product, and so on. Then there's a question of how much I should order. At this reorder point, I need to know how much should I order, which is economically viable to me. It should be above the minimum order quantity that I need to order, and so on. Right. So these formulas will give you these sort of decisions, help you take such of decisions, which can be plugged and it can be scaled to multiple products. Right. So this is how it's a typical min-max inventory planning. Right. So this is how it's being done in min-max inventory planning, but it has its own challenges, right? So the challenges can be, right, getting the right formula, right? So in each company would have different type of formulas, and it will be depend upon some expert supply chain planner. So it has some inherent bias to it, right? When we have formulas, and when you keep more
Yeah.
conservative formulas.
Hi, Hariram. Hate to interrupt you. Can we just wrap it up in 2 minutes? I think we are over the time limit.
Yeah, sure.
Yeah, thank
Okay,
you.
so I'm saying like it can conservative formulas can go to overstocking situations. So there are various challenges with inventory. So interest of time, I'm moving on for the reinforcement learning framework. So the reinforcement learning framework says where we are taking all these inputs, we take the historical demand, we take the forecast, we take the cost, holding cost, order cost, and so on cost, and pass it to the inventory agent, and it learns to take the decisions. The decision is like how much to order and when to order. So this is all done in a virtual business environment so that it does not affect the production system. So over millions of iterations, it learns for each product what should be the ideal amount of order, what should be the safety stock, what should be the economic order quantity, without explicitly programming it. So the reward that it gets, it's the cost, that the three main costs that is associated is the holding cost, out of stock cost, and the order cost. So the reinforcement learning framework that we built was based on proximal policy optimization. Uh, it's one of the state-of-the-art techniques to do it. So before that, I need to point out that it will not work for all. One agent cannot do for all of the products. So we need some clustering of products that, for one group of cluster of products which of the same price and has the similar amount of lead time, we are training one agent and so on. That's how you can scale it up to thousands of products. So this is our solution design for inventory planning through reinforcement learning. A sneak peek in how it learns, right? So for example, let's take three agents, which was trained for one iteration, 10,000 iterations, and 1 million iterations. As I said, reinforcement learning is not so sample efficient. So we have to train, millions of episodes to get an ideal inventory planning. Initially, it was, overstocking so much, but through millions of episodes of reward-based learning, it was able to stock more or less good with optimal inventory coverage and also good service levels. The benefits is definitely we do not need to it automatically knows the formulas for safety stock, and we do not need to explicitly program it. There is no bias, and it tends to perform better than mathematical models, and you can tweak the objectives. For example, if you want to have high service levels, you definitely can do that, and at the cost of, let's say, your holding cost. So it's very much customizable, and what if unless is also it's very easy in AI based learning. Right. So I would quickly move on to the demo to see this in action. So demo, so let's select any one particular product, right? So the product uses this particular agent, and we have to select the opening stock. Let's say I have 400 units of opening stock. And when I'm going to get results, we are going to see a live simulation of how the model performs and what are the uncertainties involved, what action it takes, and how it fares with the non-AI approach. So the first two graphs tells us about the uncertainties. The first uncertainties from the customer or the demand side. The forecast that is definitely noisy. We see, the forecast and actuals have a gap, and therefore, we need to account for this. And the lead time for this particular products ranges from 3 weeks to 5 weeks. Mostly we got our orders in 5 weeks, but sometimes as quick as 3 weeks, and sometimes in 4 weeks. So it's not very certain to know, like, I need to order at this point of time and I can get my product at certain point of time. So these are the two major uncertainties that the model caters to, and let's see how it performs. So these are the planning that is being done on live by the model for this SKU on this virtual business environment. We can see how much it is ordered on which week number. So the week number is running here. Next graph tells you how much is your inventory that it holds. The inventory graph that we saw earlier, it's a tooth-saw shaped curve. The formula-based model, which is a mathematical model, holds slightly higher amount of inventory than the AI-based model. Let's see. Okay, so inventory we have reduced through AI-based model, but on the flip side, let's see how is the service levels. So the service levels are pretty much, except for 2 or 3 weeks out of the 60 weeks, we are having a high amount of service level on all of these weeks. The inventory coverage, which is average amount of inventory that I hold at any point of time, is also lower than the mathematical model. So it's beneficial. So let's wait a couple of minutes for the simulation to complete, and we will see an overall comparison to see, how the AI model performed. Did it outperform the mathematical model, or did it give some other result? So meanwhile, I can take this time to have any questions.
Yeah, hello. So, Hariram, I think we are way over the time limit. So, I'm just going to direct you the questions offline and you can answer them. So, yeah. So,
Yes, sure. That's
yeah,
absolutely fine. Yeah.
the other speaker is waiting for, his talk. So I think the demo is complete by now, if I'm right.
Demo is ready now. Yes, it's ready. So we can see we have reduced the inventory by 11%, and but the service level was down by 2%. So what it decided for this particular strategy, the optimum strategy, okay, you do not have good service level because the product is cheap, or it could be other decisions, and but the reducing the inventory would more help here. So that's what it has decided. So we have 11% and 14% reduction in inventory. So this is one of the results and simulation. So yeah, as you said, I can take the questions offline. You can mail it to me. I'll be happy to reply that to those.
Yeah. Yeah. So this looks very interesting. Like I've seen the demo yesterday, but it. I think it was not trained fully, but I think I can see the results right now, and they looks promising. And I think the talk was very interesting. Like I can see some comments in the chat section which says that you are doing good work. Like Nagaro has been, you're doing good work with the Nagaro. So yeah, I think we would definitely get back to with questions, and we'll post your LinkedIn in our description so that people can refer to you. And yeah, thank you very much for your time. It was a great talk, and thank you very much for coming to PyData Delhi.
Thank you.
So
Yeah.
we're
Thank
gonna
you. Yeah.
move to our next talk, and yeah, so I think Mr. Deepak is here.
Yes, I'm just trying to share my screen. Do you need to enable something or I should be able to?
There's an option on the bottom left.
Yeah. Let me just try. Second. Okay, I think I'm trying Safari. It's not working. Let me switch to Chrome.
Yeah, sure.
Yeah, just rejoin in a second from
Okay.
Pathak.
Yeah. So meanwhile, like while the other speaker joins for his talk, I see like there are some questions in the YouTube chat, and you can definitely mail. You can definitely send us them to on our Telegram channel, and we will take them to Hariram, and he will get back to you with a response.
All right. Let me
Yeah.
share.
Hi, Deepak.
Hello. Okay.
Yeah.
You can share my screen. See
Yep.
my
Deepak.
screen.
Yes.
Okay, just let me. Do you see them in the presentation view?
Yep. I can see that, and please, can you give a small introduction about you? So that would be very
Yeah.
good for the audience.
Yeah. So the slides are not in the sorted view, right? They are in the full screen, correct?
Okay. Yeah. They're in the full screen. Yep.
Okay, cool.
Yep. Over to
Hello.
you.
Hi, everyone. I am Deepak Pathak, and I am an assistant professor at Carnegie Mellon University and also a researcher at Facebook. And I did my PhD from UC Berkeley in artificial intelligence. And before that, I did my undergrad from IIT Kanpur um, in computer science. So in today, I am very excited to talk to you about how to build robots that can potentially generalize across large number of scenarios. Okay, shall I start?
Yep.
Okay, sounds good. Okay, so before I start the talk, let me state the obvious. Generalization is the hallmark of human intelligence. So we as humans have the ability to adapt and generalize to a diverse set of scenarios. This ability makes us who we are, and this is the hallmark of human intelligence. But let us see where we are currently with machine intelligence. Well, you may all know that today we have systems that can play very, very complex state space games like Go, that can translate speech in an online manner, that can read text from images and translate languages seamlessly. And hopefully, self driving cars, the cars that can drive themselves, may not be that far, or hopefully, we don't know, right? But unlike humans, these machines are not generalizable at all. In fact, on the other hand, these systems are incredibly specific in the sense that they are trained to do one thing and one thing only. So, for instance, a system that can play the complex game of Go cannot really drive a car or other way around. And this is in contrast to humans, which where a single human can do incredible number of activities, may not be at the very expert level, but they can generalize seamlessly across number of tasks. And maybe we are asking too much by asking the robot to play Go and drive a car simultaneously. Well, it might not have very good consequences. So let me scale down and treat a very simple, straightforward problem that you might have read in Machine Learning 101, like the very simplest case of learning, supervised learning, where the goal is that given the input image X, you have to learn to output some label Y, that is which class is contained in this image. And the way we train these networks is by showing them a lot of images of a class, let's say dog on the left, and then the network and all these models are trained to output which class is contained in these images. Okay, and this the result that I am showing here is result on ImageNet, which is super famous result, and has kind of brought deep learning to limelight. And as you can see over here, that ImageNet on the test set, it has 1,000 categories, million examples, and across this very hard task, these models are able to achieve superhuman accuracy in terms of classifying which image contains what. Okay, now let's take this primary example and let us see how well do these models generalize and adapt to new scenarios. So I'll take this model, which was trained on ImageNet, and I'll test on real world. And by real world, I mean a video from YouTube, which people upload, right? But in a real world, dogs look like this. And if I try the same model on this data, it completely fails to generalize. In fact, what it does, it finds things like cobra snake in this video. It says this frame is ray fish. It says this frame is flatworm, right? So what is going on? Like the result that we thought achieves superhuman accuracy and we declared victory over this task completely fails to generalize to beyond like to a very low accuracy of 25% from 80% or even lower than this. And in fact, this is, if you ask a computer vision person, they will say it's not that surprising. And the reason is because the model was trained on images from ImageNet, which are photographs taken by several photographers across the world, where the dogs are in a very nice pose, good angle, nice lighting, and all these conditions don't hold in the real world. So these models have a very hard time generalizing. And in fact, this is the core issue that we face with in machine learning. Like whenever you start any machine learning class or book, you will find that assumption. And the assumption goes as follows, that let us assume that the training and test data come from the same distribution. And in real world, this assumption barely holds true. And in fact, it always gets falsified. And in that case, our models fail to generalize. And this notion is not just about training an image classification model on some large data set. The same problem is also prevalent in controls. So for instance, you might have seen this mighty robot videos from Boston Dynamics, which can do lots of these parallel tricks. But they fail to generalize on a mere, very simple primitive task of placing a box and lead to some catastrophic failures. Okay, falls head over heels. Okay, so right, and this is the same problem because our world is continuously changing, and in fact, this is not something new. Like, this is not a problem which we are noticing now because things are working. This problem has been from the day one, or like day zero of the beginning of the field of machine learning and artificial intelligence. In fact, let me tell you a story how old this problem goes back to. And this is historical anecdote, and you might have heard and you might not have heard it. Let me just still repeat it. So the story is about 1960s. You might have heard of DARPA. It was back then called ARPA, and they wanted to find tanks in photographs. And what to do that? So classify whether an image contains tank or not. To do that, they approached a standard procedure where they released a bunch of images of tanks, as shown on the left, and a bunch of images without tank, as shown on the right. And they released the challenge that we want to learn a classifier to find tank in images. And researchers at that point in 1960s jumped onto the problem with the best approach that they could think of, or which was state of the art back then in 1960s. And surprisingly and coincidentally, it was also perceptron back then, and it went down in between. But so what people do, they trained perceptron on this problem, and they achieved very superhuman accuracy, like really, really good accuracy. And even at that time in 60s with this very few images. And okay, they were very happy, they submitted the result. But when the results were tried, and as the general wheeled out a real tank, all those approaches completely failed to find the tank in images. Any guesses why? You can unmute if someone is here. Just wait for 5 seconds. Okay, it's a YouTube live, so we can, maybe guesses are on the chat. So the reason these approaches completely failed is because if you notice that the tank in the real world, it can be an arbitrary situation, and all these data sets were of photos of tank which were taken in a clear day, good sunlight to get the good photograph, while the images of non-tanks were of clouds, forest, and they were cloudy, foggy, and not maybe in bright sunlight. So what the network just learned, it cheated to only find the threshold of contrast and never really learned to find tank in images. So my point from the story is that no matter what you do, no matter how cleverly design the task, the computer, if you're trying to minimize an objective function which is defined by your data or your labels, in fact, not data, it will always find the shortest way to find the solution, and it will always, and it can cheat, which in ways that you might not have imagined before. So how can we prevent computers from cheating, and how can we make them generalize? So to study that, let me take a task over here. Let's say that the task over here is for this robot is to tie knots. Okay, so it's a fairly hard task because knots are deformable. So let's say given this shape of knot in the beginning, the robot has to figure out how to tie this knot. And what it has to do is it has to output a series of actions that lead from the current, original image to the goal image. And all it sees is this image of the camera. Okay. Now, how do we solve this problem today? And how can we go about solving this problem? And in today's talk, I'll present some approaches to do that. Okay. So currently, the most popular approach to robotics and solving and building robots is imitation learning. And this is the most famous way all the robots build your car in industries, etc., etc. Right? So what is happening here is that what happens here is that an expert gives a demonstration by controlling the robot manually to give you a series of actions which are to you to apply to achieve some task. And this is very tedious for the expert, but more importantly, this is specific to only one goal. Like, you have to repeat this whole procedure for every and each goal that you see in the world. Okay. So, and there are some approaches we can do it with few few demonstrations, but they still require a lot of demonstration at training time. The other line of work is reinforcement learning, and the previous talk talked about a lot of details in reinforcement learning. I'll not go into that much detail, but the general idea is as follows: that given a current image, you want to train the robot's policy, which can output actions such that if you apply those actions over time, you slowly reach to the goal image. Okay. Now, how do you train this policy? The way you train this policy is by giving reward. So if it reaches the goal image, you give it a candy. Like, okay, take your jackpot here or take something. And then the policy is trained to maximize this reward over time. And in the beginning, the robot does not know how to perform any task, and so this policy starts being random. Now, if you think about this problem, you get a candy when you tie the knot at the very end. And if your policy starts being random, how likely it is for the robot to randomly tie the knot such that it can receive the candy? Right? So it's a chicken and egg problem. You to receive the candy, you have to reach there first, but you don't know how to reach there. So it's a very random process in the beginning. And in fact, in this case, if you were to randomly stumble upon this goal state, it will take these many interactions to just reach there once. Right? So how can such an idea be useful to anyone in any case, in any scenario? Well, in fact, the way you make it useful in practice is by giving dense reward. So for instance, you might have seen all these games that, oh, this AI can play this complex game by looking at pixels. But the key insight, or the not even insight, the key reason that these agents are able to solve this game is because they are looking at the score of the game. And they're getting a very dense supervision at almost every time step via dense reward. Like even in task of navigation, where the goal is to reach some goal location, most approaches shape the reward function by adding these apples in between. Like what are these apples doing here? Like they are trying to give you intermediate rewards, and where the goal is to reach some location in the maze, right? This is completely fabricated way of giving the reward function. In fact, there are no apples in the real world. In real world, the reward could be sparse or delayed by years and years. For instance, like how does this child over here know how to act such that she can become fighter pilot many years later? Right? Do we backprop the objective function of rewards from 20 years into the future to the state of this kid? No. So how do these kids even work in this very, very long horizon scenarios? Well, as psychologists like to argue, the way they act is by using something called intrinsic motivation or curiosity. For instance, you see a kid happily playing with Legos. This kid is not trying to minimize any goal or maximize any reward to go to MIT in the future or go to or do PhD from Berkeley, right? This is basically driven by no extrinsic goal and by his own curiosity. Can we use the same trick? Like, can we can we remove the notion of external goal in our agents? Because if there is no goal, the computer can no longer cheat to find shortcut because there is nothing to find shortcut for, because you don't have a goal to optimize. Correct? You don't know the goal. And in fact, this notion of learning without goal is just not for baby. This is popular in animal kingdom as well. For instance, this example given by Lesson Gopnik of chicken and crow. Like these crows are one of the smartest birds on the planet, and they are generalists. They can do lots of things, and they explore. While while chicken, on the other hand, are one of the dumbest bird on the planet. As soon as they are born, they have a goal, and the goal is to peck for grains, which focuses them to be very narrow in the things that they can do. While these crows spend long time in the childhood without goal and just doing exploration on their own. In fact, this notion of exploration or goal-less exploration is heavily tied with intelligence measure of a species. Like on the y-axis is how intelligent the species is, on the x-axis and how much time do they spend in the childhood. And there's a strong correlation, as you see over here, that the longer the weaning period, which is childhood effectively, the intelligent the species is. Okay, so this leads to our first hypothesis that if we can somehow remove the notion of external goal, this probably will force the agent to learn skills that help it generalize, because it cannot cheat to find the shortcut. But now the question that we are into the bigger question, like if you do not have any goal, what do you even do? What does it even mean to act or learn without goal? Okay, so before I go into robotics and robots, let me first give you a bit of intuition. What do I mean by learning without goal, and what can the agent do if there is no goal? And we'll start with very simple environments, like let's say this game of Super Mario Brothers, which you might have heard or played of actually in your childhood. And it's like very simple game, like the agent has some observation and it has some action. And my agent sees the observation on the right, and then it can take any of these actions, right? Now, in the beginning, you can press left, you can press right, it just goes to the right, you can press up, it goes up, down, nothing happens, right? Now, the key idea that we'll follow is that our computer will try to build a model of how the world works, right? Okay, so for instance, over here, like from the previous data, it will try to build a model of what will happen if I do this, if I do X. So for instance, in this case, the agent, before it takes the action, it tries to predict what will happen. So given the jumping action over here, the agent predicts if it presses this button, it should go up and then come down, like what happened in the previous frame. Now, in reality, if the same thing happens, the agent becomes happy and its belief gets reinforced. Okay, but positives that don't give you as much of a signal to learn. Well, in some scenarios, for let's say over here, now let's say the agent again predicts, okay, if I press up, it will go up and go down, right? Because that's what happened in the past. Now, in this new example, because there is a pillar, the agent will go up, but will not come down. And its own prediction will get violated by its own actions and it will incur a prediction error. Now, our key idea is to phrase this notion of curiosity, like what we saw in the kids example, that they can learn on their own, is by exploiting this prediction error. So you can define curiosity of the agent by its ability to predict. Okay. Just to summarize the idea, the key idea is as follows: that agent first begins by doing random actions. It builds a model of what will happen next. And then it uses the model to predict the consequences of its own actions. Okay. And then whenever its prediction error is high, the agent gets more curious. And now the key part is when it gets more curious, what it will do is it will go back and explore even further to collect more data. And as it gets more data, it will use the data to improve its model. And when the model is improved, the error will go down and the agent's curiosity will go down. So it has to go somewhere else to be curious. So now what you can see is like there is a sort of a chain reaction going on. Even without any external goal or any external signal, the agent can always continually learn in trying to find actions such that its model gets better and better over time. Okay, and the agent's policy and model supervise each other in this continual scenario. In fact, many people before this have proposed several versions of exploration. But the key difference in the prior approaches is that most of these approaches were in the context of some extrinsic task, like going to MIT or going to Berkeley. While in this case, our agent does not have any external goal, and it is learning completely on its own. So no reward, only by being curious. Like for instance, in the same game I showed before, we'll hide the notion of rewards. So we'll cut this off and do not see any reward. Much like probably like I also played in my childhood. I never really saw the score. I did not even know for a certain age that there is a score in game, Mario Brothers, and many people I've talked to say the same thing. So in the same spirit, we'll remove the reward over here. And in the beginning of the training, as you can see, agent is just jumping around and not doing much because doesn't know what to do. It doesn't have any goal, right? Okay. Now we let it do these things for a while, and after a while of curiosity-driven learning on this game, what we see is this kind of behavior emerges. So as you can see, without even knowing what the game is about, without knowing the goal in the game, the agent can just discover all these interesting behaviors of crossing different levels, killing enemies, jumping through pipes, and it keeps on going and going and going, even though we never ask the agent to solve any task or do anything in this environment. It's just doing it on its own. And it goes much farther than I could go in my childhood several years back. And the behaviors like jumping pipes, killing enemies, they just emerge from its own curiosity. And the reason is that the agent wants to be curious. So if enemies try to kill if the agent dies, the curiosity, it can no longer be curious. So it wants to stay alive to be curious. And if the enemies kill the agent, it tries to kill them so that it can remain alive to be curious. So it's kind of a chain reaction, which you can see the argument of why it leads to these complex behaviors the longer you train. Okay, and this is not just for this game. You can apply to almost any set of reinforcement and tasks where these things are applied to. But the difference is we do not have any reward. So it's completely unsupervised. You completely remove the notion of reward, and it is driven by completely on its own. You can also put agent on two sides of the same game. It learns to play and maintain a rally for very long. You can also put this on robot like this ant over here, and it can learn this fidgety walking like behavior because it doesn't have a goal. So it doesn't run anywhere because there is no reason to run anywhere. It just going around slowly to and learning to walk as a byproduct of being curious. You can apply this for navigation as well. You can drop an agent in any 3D scenario, and all it sees is this image, and it learns to navigate and not get stuck inside of scenarios. And the same skills can also generalize because they are not trained without goal, so it doesn't overfit to any intricacies of the environment, and can quick and seamlessly generalize to new scenarios and new textures at test time without any further training. So it does get stuck sometime. For instance, like in this case, if in the navigation task I add a television and give the agent a remote of the television, it starts and this always changes channels on TV and never leaves it. Well, in fact, if the agent does not have the remote, then it can avoid it. For details, you can see the paper. But when it has the remote, it cannot distinguish whether it's the agent that's making itself curious or it's the environment making it curious. And probably, yeah, watching TV is fine as long as you don't control the remote all the time. Okay, so okay, these were just simulation and environments. But what about curiosity-driven learning in real robotic scenarios? And here is one result of our first attempt at applying the same idea to the real robot settings, as you see over here. And it goes wrong in a very horrible manner. It just starts doing stupid things. So why? Like what? Why? So it completely failed in this scenario. And why did it completely fail? Well, it's not very surprising because the approaches that I just described still require a long time to learn because they are they're learning about curious things by acting in the world and figuring out what to do. So it still takes a long time. And while in real robot, the same amount of time will take like to spend the same amount of time that you can spend in simulation will take years and years just to get one experiment right. Okay. So in this case of learning with curiosity, we still removed the notion of extrinsic reward, but why were the results still inefficient? And for explaining that, let me go into a bit more detail about the approach. So the way I described the approach earlier, that the agent sees the current image and it wants to act to output some action to get the next image. And the way we defined curiosity earlier is by building a model, which is a prediction model, given the current image and the action, predict what will happen next. Okay. Now, when you predict something and you take the action, you compute some reward, which is your prediction error, like what you predicted and what was the actual truth. Now, if you notice over here, to compute this actual truth, like this xt plus 1, you actually had to act in the environment, right? Like I push an object. So I have to act in the real world to push the object to obtain the next state. So this state is complete black box. You don't know how the real world works because we don't have a model of the real world. If we had a model of the real world, then we are already done. You don't have to do any of this, right? So this is a black box reward function. So we have to still use the reinforcement learning operator to optimize this black box thing. And reinforce is more of a hit and trial optimization. So it still takes a lot of so it's the right thing to do in expectation, but it takes lots of samples to estimate the correct expectation, and it suffers from variance issues. Okay, so it's very inefficient and takes a long time. And this is probably one of the reasons that the approach is so inefficient that it cannot scale to robots directly. Now, what we do over here is that we'll make one small change. I just change the idea from prediction error to something else, but very small change. And the change is as follows. Instead of building one model, let's build a bunch of models. They are trained in the same manner, that is to predict the next state. In the same way, they minimize the prediction error, and they are trained together to learn this. The parameters are trained to minimize the error. Okay. Now, but the one difference is that we'll change the notion of curiosity from prediction error to the disagreement between these models. So we'll just, the variance of the predictions of these models is your intrinsic reward. Now, I'm no longer saying your error is the curiosity. What I'm saying is how much you disagree is the notion of curiosity. And this is these two notions are very similar. In fact, in an unbiased case, they are the same thing. But in a general setting, this has some advantage. And the advantage is, I'll show in a minute. One advantage is as follows: like if you have multiple models, and let's say the scenario of noisy TV, where the outcome of your actions is completely random. Like I can pick some channel and it will show me a random thing, right? And I can never learn a good prediction error. But if I'm learning an ensemble of models, each model at some point will go to the mean prediction, like what's the mean of the distribution. In which case, the variance between those models will drop, and the agent will get unstuck because its curiosity will drop. While prediction error agent will always get stuck. So now we can actually solve that problem, which I described earlier, where the agent gets stuck in watching television and it can make progress. But a bigger advantage of this approach is that if you notice that the variance of these outputs as I show over here, actually this variance has no xt plus 1 over here, the red thing that I showed earlier, which has the issue, because you don't have to act in the world to compute the next state. So this objective function is fully differentiable. It does not depend on the environment. It's just the model's disagreement. So you can just differentiably optimize this without using the reinforcement operator. And this becomes very efficient. So before I show a result on the robot, let me first show how do existing approaches explore and collect data in the robotic scenarios for robot learning scenarios. So for instance, this is an example of random exploration, which is the current most popular approach to collect data. But as you see over here, these robots, if they explode randomly, they don't even touch the object for a very long time. So how do you still see like lots of papers from all these big labs like Google, etc., etc.? Well, the trick is they put lots of object at one place such that the robot can still grasp something, even if it is acting randomly. And to make it more efficient, they have hundreds of robot or inefficient, whatever you can say, right? But in academia, it's hard to afford hundreds of robots and this robotic arm farm. So we have only one robot, but we instead have this curiosity-driven learning setting where even in just few hours of learning, the robot starts to do some interesting things. It starts to pick up objects, it starts to throw them, it starts to collect data which is interesting which can be used to build models to do planning at a later stage. Okay. So far, I talked about how can agents learn and show interesting behaviors without having any idea of what the goal is, and completely driven by its own intrinsic reward. Correct. But how do we go from this self-directed notion of exploration to achieving goals? Because in the end, I want my robots to be useful to me to achieve some task. Correct. Okay, so how do we do that? Well, the idea is very simple. We'll just use the model that the agent has been building this whole time, because the agent is using the model to act in the world, like model of if I do this, if I am here, what will happen next? We'll use the same model to plan. And I'll not go in the details of how do we do that, but it's a very simple idea. You can think like agent sees a state, like the example I showed in the beginning, like this image on the left, and it wants to go to the right. It just all in imagination, it takes the model and it tries to unroll the consequence if it takes different actions. And without acting in the real world, only mentally it can optimize for the right set of actions because it has a good model of if it has a good model of the real world. Okay. Now, so the idea basically goes as follows: that agent starts by exploring the environment. It collects data from this environment. It collects data via exploration. It could be curiosity, it could be some other ways, but it distills the data into models. And then at test time, you want to go from achieving at test time, you are given a goal image and you optimize for the goal image via planning with this learned models. Okay. Now, so this paper actually came before even the real robot paper. So over here, what we did was we took a pre-collected data and we built the models. And now using the model, which was built from its data, which was collected without any extrinsic goal, the robot at test time is asked to achieve several tasks. So the same robot is now asked to generalize from its training time data, which had no goal, to several goals at test time. So it's a generalization task again, right? And our hypothesis is that since the agent is trained without goal, it should be able to generalize better to new things. And in the paper, we show all these tasks. But let me show this not time task, which I showed in the beginning. So the way it works is that test time, a human comes and shows only one example of, okay, how to tie a knot. And note this, robot is not even trained on this example. Directly at test time, just by looking at one example and no actions, only the images, it can achieve the same task on its own. And this is not just manipulation. Even in the case of navigation, we do the same thing. We leave a robot to first explore in an environment, and for several days, we just put it in an office, and it goes around and around 24/7 for 15, 20 days. And it collects a data and builds a model. Then at test time, we take the same robot, put it in a new environment, and does not and ask it to solve this task. Go from this image to this image. This is a robot's view, and it's a new environment, and it does not have access to map, so it's completely mapless navigation. It can do these simple tasks of going from one image to goal image. There are several approaches which you can leverage to solve this task, maybe using shift matching and things like that. Uh, but note that the key part over here is that we are not training for this task. This behavior is completely emergent, and it's happening and it's happening completely out of you know completely it's emerging completely out of agents exploration. Okay, so far, one thing I have been hiding under the rug, and that thing is that in all those approaches I've been talking about generalization of from one task to other task and showing behavior and showing at the same time and at the same robot at test time. So if you really want generalization in robotics, it cannot be for the same robot because every robot is different. Like, you might have built some robots in your lifetime, and every time you build the same robot, they are somewhat different, right? In fact, this task of generalization across robots is extremely challenging. For instance, these like in my 1 minute of Google search, I could find these many types of robots, and every lab in the world has a different kind of robot, right? So can we generalize across robots, or can we train a single policy that can work across all these robots? Right? This is a very challenging problem. For instance, this robot is a NASA dexterous manipulator, and if you see how many motors does this robot have, like nobody might even have this robot. So how can we even think of generalizing something to this kind of robot, which we might not even have seen at training time? So let's see how do the existing approaches like RL, etc., work for how well do they generalize for robot control? And in fact, the 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 key conclusion from several of the papers that they don't generalize. So you still have to tune a lot for reinforcement learning policies to make them work across one setting, like one of the agent over here. And if you make any minor changes to the robot, like I just removed the 1 feet on the right and like just the bottom feet, and they completely baffle and just completely fall apart. While this is not the case in humans, like we can still walk on one leg and things like that, right? So the goal is here is can we train a policy that can work across several of the robots, such that at test time it can also generalize to some unseen robots. And this problem has been tackled in the past, like as you see over here, some of the papers. But as you see in the image, they try to train a single policy across all these robots, but they all look very similar because they usually share same topology. And if they don't share the same topology, like in some of their works, like NerveNet, they still have to train different policies for different parts of the robot, like for one for limb, one for torso, one for root. So it's very complicated, right? What we ideally want is a single policy that can work across lots of robots, and a very simple and key idea to solve this issue. But before I go into the idea as to how do we go about solving this problem, let's first analyze, like, why is it even possible to have a same policy that can work across these two agents? Like, Walker is very different. It has two legs, very different shape. A humanoid on the right is very different. It's a lot more number of motors. Why should we be able to train a single policy? Okay? And in fact, in this work, we just don't train on one or two robots, we train on a bunch of robots together. And our hope is that once we train on all these robots, this can generalize to new tasks. And this becomes very challenging because each robot has different number of limbs and motors, different number of actions, and not just number of motors. Every robot has to show a different behavior. Like hopper is like a stick has to hop forward to move forward. Uh, a humanoid has to walk. A one-legged humanoid has to also hop. So these are different behaviors which needs to be modeled. And why should a same policy be able to solve all these tasks in together? Like, is there any evidence that we have from nature that these things are even solvable? And in fact, yes. So this is a slide from Bob Full from 2000 lecture. And what the argument here is that even different species like humans, dogs, crab, cockroach, they have very different shape, very different gaits, but the pattern of force that they apply on the ground is actually shared and similar. So there is some hope that there could be a shared locomotion uh, um, policy possible. In fact, in this case, as I'm showing over here, there are some animals which sort of are born with this zero shot controller, zero shot policy, that as soon as they are born, they can start to walk. For a giraffe, these are called precocial and super precocial animals, which are, and this is maybe some evidence that there could be, it could be a possible solution to solve one policy that can control all these robots together, as I see, as I show on the screen. Okay, so maybe it's okay, it's possible. So let's see how do we go about solving it. So what's the key idea? So the key idea is as follows: like instead of training a policy for the full robot, because robot has different shapes, etc., etc., what we propose in one of our previous work is that the policy is shared throughout the body of the agent. So every motor has a policy, and then you share the policy across, and you share the policy across all the motors. It is all the limbs of the agent. Okay, so it's modularity. The key concept over here is modularity uh, at the level of the hardware of the robot. Now, okay, how do we apply this idea to the current problem that we are talking about? Training a single policy for all these robots. So what we do is very simple. We take all these robots, and for them, for each limb that is motor, we share the policy everywhere. So it's a shared policy. Uh, and then we share the same policy, not just motor of one agent, but all the motors of all the agent. So it's a single policy, single parametric function, which is shared across everywhere. Okay, now you can do the sharing everywhere, but does this idea work? Because same network is applied at different locations of different agents, like in Walker and Hopper, the same policies applied to torso, head, and foot. Will the same idea just work out of the box? Well, not quite. And as you see over here, if you just apply it and train it, it doesn't work at all. And the reason is because since the policy is shared everywhere, the policy has no idea whether it's controlling hand or it's controlling leg. And it cannot decide which function to perform at what location because it's completely shared, correct? So there is no global coordination. It's a completely decentralized system. Okay, so how do we fix this issue? Now, the way we fix this issue is as follows: that we say, okay, the input and output are different shapes. The input can be any, like it's perception, touch, etc. Output is some motor actions. So what we do is to decide how to give context to a policy, we pass an extra vector as input, and the policy modifies the vector and passes it output. And the key thing is that these two vectors lie in the, sorry, these two vectors, x and x prime, they lie in the same dimensional space. Okay. Now, since they lie in the same dimensional space, I can copy the same policy for each motor, as I show here. And since the dimension of these vectors is the same, I can just pass the output message of the child node to the parent node. Okay, so this is like treating these networks as Lego blocks, where these messages or these vectors are acting as hook of the Lego block. Because Lego blocks, you can put them one over other. Like you can put two Lego blocks at the bottom of one another or at the top of each other. It doesn't matter. Any ordering is fine because they have the same hook, and these messages act as the same hook, and you can shuffle them arbitrarily. Like if there is one robot which is this at training time, at test time you show a new robot shape, you just cut this policy from here and you paste it at this new location, and you just pass the message of the child to the parent. Right, so you can reshuffle your Lego block modules in arbitrary manner at test time. I hope this is making sense. It's too late in the talk, so let me
Yeah,
do it. Yeah.
yeah, it does make sense, and I think yeah.
Okay. Cool. So now the one last thing is, now since these are messages, how do you pass them between nodes? Well, what we do is very simple approach that you pass messages once from leaf to root node. So note that this is the shape policy shared everywhere. So you can think of it as a graph, and the graph is undirected. So it's a tree basically. You can pick any node as a root node, and the other roots are leaf nodes. So you transfer messages from leaf to a root node, and while you are coming down towards the topological ordering, then you output actions of these robots. Okay, so the messages go from bottom to up and then top to down, and while coming down, the each limb or each model outputs their actions. Okay, so let me move to the results. Now, as we see over here, earlier, as I showed, a single policy was having hard time to generalize. And now we are able to train a single policy that can control all these agents together. And if you see, they show very different behaviors, even though the policy is shared everywhere. Like as we see over here, again, like this policy at the bottom, it hops, this policy walks, and while it's the same policy shared everywhere, the same policy at the hand, same policy at the foot, same policy at the torso. And for instance, if you see over here, it the same policy, just because the agent shape is different, it itself figures out which kind of gate to follow, and it shows very different behaviors across these agents. Okay. Now again, why were we doing this in the first place? Well, our goal is to train a policy that can not only work across multiple robots, but also generalize to new robots. Correct? But does it work across unseen robots? Okay, let us first see some held out robots. So we never showed these robots at training time, but they are from the same distribution as I showed earlier. And as expected, they can also work and walk and show different gates. But what about uh, testing on very out of distribution robots, which their policy has never seen before? And as we see over here, across very different robots, it can still do interesting things. So as you see, it doesn't excel like because it has never seen the robot, it never trained on them, but it can still maintain balance and not fall. So as you see over here, like this discovers a completely new gate at test time without even being trained on it. And this policy has very heavy hands and can still try to walk forward without ever being trained on this. It has never trained on this, have several legs, blah, 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 like many things. You can also add objects at test time, and it doesn't, there was no notion of objects at training time. I showed the training time results, but it can still maintain balance and try to move forward despite not being ever trained on these things. And again, the same policy is shared at all the limbs that we see over here. It does some finicky things. Well, it does fail at times. Like if you really make the agent very heavy, for instance, this is like some very heavy agent. Muscles are not that powerful for the agent to lift it up, so it completely fails. On the right, it has no legs, so it tries to use its hands to move forward, but again, does not really succeed that much. Okay, then this is the last part of my talk, this last slide. Now the question is, does this, so far what I would show in the results that the policy is completely decentralized and only messages allow it to control or show different behaviors across different agents. So this is some evidence that there is some coordination emerging between agents, because if there was no coordination, it would not hop and walk across different agents because it's the same policy, correct? So there must be some coordination emerging, but can we actually analyze it? So what, and like we analyze the coordination in humans or in insects, like these patterns that are there, central pattern generators. Okay, do we have something like that emerging over here in this case? So what we do is we just visualize the messages of the root node when they are going down. And this is 1D projection of the messages in an episode. Now in the beginning, they are all zero. There is no change in the line. They're all zero because there is nothing happening. They have not trained yet. But as you train the agent, these messages start to take some interesting shapes. Like as you see over here, it starts to take 2 peaks, 3 peaks. And when we found, okay, these peaks start to correspond pose of the agent in the walking shape, like in the walker in the top case and hopper in the bottom case has three peaks. And this pattern is emerging between policies, even though policies are shared everywhere. These patterns are emerging completely on their own to guide the agent. Okay, is it scalable to real robots? Well, or even are there robots in the real world where you can apply this? So in fact, there are several modular self-assembling robots already in the real world. And at UPenn, MIT, CMU, there are several of the labs which have these robots. But the difference so far in the literature is that the software for these robots is hard-coded, or somebody is controlling them manually. But we are learning a software for them as well. And in fact, we are also trying some of these things in locomotion, or we are planning to try some of these in locomotion. As you see over here, this is a robot at fair, where the motor is also shared everywhere across the robot, and we can apply the same idea to this robot, for instance. But I don't think the motors have to be same across the robot for this to work, because humanoid has different motors than walker, and it does fine. Okay, so just to summarize the talk I showed today. So I talked about a couple of directions which can allow us to build embodied intelligent agents, which can generalize to new scenarios. So one was generalization across software, that is tasks. The second is generalization across hardware, which is robots. So for software that we shared, okay, it's difficult by training on one task. Let's train on without goals and with curiosity and plan at test time, and we showed some results. And for hardware, we the key idea was to train a policy which is modular. So curiosity and modularity are the two ideas I talked about today. And modularity allows us to generalize across robot hardwares. So these are, I would say, we are barely scratching the surface, and the results are really, really early what they could be, but they're still promising, and still a long way to go. And it's nowhere near being solved, or even the beginning of the solution. And thank you. And code and all the details are there on our website. And yeah, I'm happy to take any questions now.
Yeah, all right. So first of all, thank you very much for the talk. It was so interesting. Like, I think the whole team was into the talk, and we were super engaging talk.
Yeah, thank you.
So yeah, so we have questions. Like, we have a bunch of questions for you. So I'm sure you're ready for questions.
Yeah.
Okay, all right. So if you want, you can turn off your screen share if you want.
Okay.
Yeah, great. So I'll start from the bottom, like the last question. So the question goes something like, does this applications have something to do with chemistry, biomedical domains to explore protein molecular structure, etc., through exploration?
Yeah, that's a very interesting question, and I've been thinking a bit about it in the last, at least in the second part of the talk that I showed about, like modularity aspect, because the inherent idea of sharing same policy everywhere, what it is allowing us to is find patterns through a very large state space. Because if you're training a single policy across 20 plus or 30 plus robots, it's a very huge state space. And with current approaches, it's already very hard to train on one robot. So, and protein folding and all these tasks have really high search space to discover. So I think the modularity idea is, I guess, applicable or should be. I think it should yield some promising result in that search. You can combine that search process with curiosity and exploration as well. We haven't merged these two directions into one yet, because yeah, it seems, at least for the robotics, it seems very hard to attack right now, in the sense that robot has no goal and not even a body. So and it's trying to find both of them. So yeah, but I think at least protein folding and biological domains should provide some good application for both the directions.
Yeah, makes sense. So thank you very much for the answer. We'll move to the next question. It is okay. Yeah. So do the robots show negative behavior learned at times when trained with no curiosity or no objective? And in what ways can the input data be biased?
Wait, so when there is no curiosity and
Yeah.
no external goal,
Yeah. So what are the negative effects for that?
so you cannot do much, right? Like in the end, at the end of the day, what does training mean? Like training means like updating the weights of the model.
Yep.
Now to update the weight, you need some objective function.
All right.
And the argument I was giving was against having an extrinsic objective function, because whenever you design some extrinsic objective function, like as a human yourself, you'll always be biased in one way or the other. Maybe not intentionally, but unintentionally you can be biased in arbitrary ways. And the hope is that, with this curiosity kind of thing, your objective function is intrinsic. So uh, hopefully you will learn things which are not biased. uh, and without having curiosity, you at least need some objective, right? So you can have different formulation of curiosity or different formulation of exploration, but you do need some exploration or some objective to optimize the parameters. Yeah, I'm not sure I completely got the question of no curiosity, but I think I I hope that I explained that why it's not possible to do without
Yeah.
anything. Like you need something. It need not be curiosity. It can be something else.
Yeah. Cool. Makes sense. And the thing is like, just a second. Yeah. So are there any ways the input data can be biased?
Oh, are there ways the well, yeah, there are several ways. I think the input data can be like as long as you design your data, it will be biased. I would say, I would make a stronger statement. Like like in the tank example I gave,
Yeah.
or the InvestNet example I gave. So
Yeah.
input data will always be biased, and I think what we ideally want is the agent to find its own relevant data. So there should be continual learning. Allow the agent to discover its own data on its own.
Yep.
How to make it practical for non-robotics applications? I'm not super sure about that. I don't have a good like for, let's say, image classification. Do you learn on YouTube? Do you learn on Flickr?
Hmm.
It's hard to say because all of these sources will still be biased at the end of the day.
Exactly. Yeah.
Yeah, so it's very hard to remove bias completely from any learning process.
Yep.
As long as it's passive learning. But if it's active learning in the sense that there is some embodiment and the agent can collect its own data, it should be possible to. That might be one way to handle the bias problem. Or like protein folding example. I don't know. Maybe in that case, if you allow the agent to search the full state space, it can probably come up with some, like, because some of them are closed world problems and some are open world problems. In the open world case, it's kind of hard to avoid bias altogether, I
Yep.
suppose.
Yeah. Makes sense. All right. So moving on to the next question. The question is: are we modeling some kind of consensus between the multiple RL agents to develop the degree of curiosity for each agent?
So is this?
Should I repeat the question?
Yeah. So I'm trying to. The question doesn't quite make sense to me, but I'm trying to find the closest
Okay.
projection in like.
Okay. So
uh,
the question is something like: are we modeling some kind of consensus between the multiple RL agents? So I think we have placed different policies on every motor of the, what do you say, locomotive motor. And so is there a consensus between multiple RL agents to develop the degree of curiosity for each agent?
I see.
Like,
So okay. So
are they?
in the yeah, I got it. I see. So
Yeah.
there are two interpretations of the question. So okay, let's take the first one which you just mentioned. In
Okay.
that one, the second half of the talk where the robots were walking,
Hmm.
they were not curious. Those robots had the goal of walking, but what we were doing, they were discovering their own structure throughout the body. So they were self-supervised in that they're modular, correct? And in that, yes, there is some consensus which is developing throughout the body of the agent, because even though the policy is shared, and the graph I showed at the very end of the talk where this pattern emerges, uh, of like this sine wave or three peaks, or not sine wave, like three peak wave or two peak wave, that's some evidence of that there is some consensus which is evolving, even though the policy is shared at all locations, uh, which is an indication of global coordination. The other interpretation of the question is what I showed in the very beginning. Like you can put curiosity on two sides of the same game, and they learn to play the game of like ping pong, of like maintaining the ball. And there is, in fact, it seems like there is some consensus which happens, and then that is happening So in that case, the policy was not, or some part of the policy was shared. But the reason I think the consensus is happening in those cases because the platform is the same. The same world is shared by two different agents, and if they both want to be curious, they have to figure out a way to interact or have some consensus to make progress in that world. So which is like, from psychology perspective, you can think of it as theory of mind kind of direction. But I would not claim that they have theory of mind. It's not that. I would not claim that, but it's along that kind of direction.
Okay, all right. I think that answers the question sufficiently. So we have next question. It is in a real world scenario, how do we measure the curiosity of the agent? Is there a metric or?
Well, so the question is that measuring curiosity by itself is not a very good measure or evaluation of the agent, because we didn't make agents curious just because so that they can be curious. It doesn't mean anything. It does like everyone can be curious in their own way, right? The main point I was trying to argue in the talk is that it's a good way for the agents to be general purpose so that they can achieve new task at test time more efficiently. So for instance, one way to measure how good your curious agent is to see the end task performance. So I take the agent's model and I plan for end tasks, like the not time task I showed, or a total, or the navigation bot trying to achieve some goal image or go to the goal. So you can see how, if you have two agents which have different methods of curiosity, for instance, you can test them on some common task and see which of them adapts to the new task better. In some scenarios, you might be able to measure, like even without planning for new tasks, they may still discover some behaviors. Like in the game scenarios, Super Mario, it learns to play the game without planning. It just learns because it is trying to explore, right? So, that act as a proxy to measure the degree of, okay, this agent is probably better, curious in a better manner compared to the other.
Yeah, that perfectly makes sense.
Yeah.
So let me just look at the next question. Yeah, so the next question is, can we use some of the classical AI techniques to limit the search space? And if yes, are there any downsides to this approach?
So yeah, so classical AI techniques. So we are thinking of. So we just released one paper, which is called sparse graphical memory, a few months back, and it's on my website and also on archive. And so one part where you can use of the classical approaches, and probably you should, is the part of planning. Like once the agent has built the model, in order to plan for new tasks, you want an efficient transfer from exploration to achieving goals. And it's kind of too hopeful to say that the model that you're learning would have captured everything about the world, and that model is sufficient to just plan for the new task. It's just kind of an overstatement. So what you might want is like the model can have some parametric function, like a function, or and has some non-parametric part, like some memory. It is storing a graph of what is it has explored before. Now, for planning stage, going from this exploration data to achieving task, you can use graph search methods in the experience the agent has already collected to figure out what are the best sub goals to achieve or sub goals to decide such that I can reach this eventual goal. And over there, these classical methods and in that paper, for instance, sparse graphical memory, we try to talk about how can you combine some of these classical techniques with modern reinforcement learning, etc. approaches so that they can adapt better at test time.
Yeah. All right. Thank you very much for the answer. And let me see if there are any questions. Okay. So I think like we don't have any questions on the YouTube chat, but I do have a question of my own. Like when I was listening to your talk, so it was something like when you showed us the Super Mario example, in which the agent was learning on its own, like exploring on its own the environment, and there was a moment when when the Mario was jumping up, and there was a, what do you say, he jumps on the block and it rewards him with a coin. So that is a process where that is a process which is like of a high curiosity, as compared to a process in which he tries to run into a wall or just standing somewhere. So I was just wondering that is there a case that the agent might get stuck on that area, on that part, just because of high curiosity? And is there a scenario in which the agent would develop some kind of pseudo goal, because we are not giving him an external goal? So is it a possibility of getting stuck, or, and if yes, and is there a possibility of uh, creating a pseudo goal by the agent itself that would go sideways? And I mean,
Yeah.
so
So
did I?
like in the at least the Mario example, like so I think in the beginning, yes, it does try to get a lot of hit the wall and then see what happens, right? But if you keep doing that, it's not very hard to predict, like the coin thing, for instance. If you hit it, you get a coin or something, right? So it learns so that the key thing here is that the agent is learning a model in an online fashion. So it's not just stuck, in the sense that if it's getting more and more data, and if the data is predictable, it will get unstuck because the model will improve, right? You're training the model simultaneously. So when the model improves, the error goes down, the agent no longer is curious and it can do other things. But it does get stuck in some scenarios when it's impossible to predict, like the TV example, for instance. Like it's, you always see some new thing, it's very hard to predict. So in that case, it does get stuck. But then the way we get around that problem, as I showed after that, is by modeling disagreement and not the error. So if something is too hard to predict, your error will never be zero, but the disagreement can be still be zero, because everyone will say, okay, I give up. I think it's 0.5 value, not zero, not one, it's 0.5. Everyone says 0.5 because they all gave up. So their error is remains 0.5, but their disagreement is zero because they all have given up in some ways. And so it gets unstuck in that case with that idea.
Yeah, and is there a possibility of developing a pseudo goal, like
Oh, okay. Yeah. There is, so this is one way, like this curiosity and exploration is one way of going about exploring without external goals, by building model and then checking how well the model is doing. There are other ways as well, like the agent can try to generate goals for itself, which can probably, I think, you can call pseudo goal in some ways. And there are some papers in that direction from Berkeley as well. Yeah. However, there is one challenge in that part, which I think is as follows: that if you are trying to generate a goal, you ideally want a goal which is not too hard and not too easy, like right outside of things that you can do. Like if I set a goal for myself to go to Mars, for instance, right now, it is just too hard, and I'll completely fail, and then I'll not learn anything. It's like it's too hard to be useful. If I make a goal of very simple, can I walk from here to the left? It's probably too easy for me. It's like, no, it's not very useful again. So how do I know which goal is the right amount? Like today, I'll try to solve this math problem, for instance, like something which is right outside my thing. And humans are able to do that, surprisingly. We don't know how. So there is psychologist Laura Schulz at MIT. She studies this some of these things, like how do we come up with goal hypothesis, and it's unclear. Yeah, it's, I don't have a good answer to that. How do we do that? Because there are many factors. Like we are not like blank slate when we are born, so it's like hard to say. Yeah.
Okay, all right. Yeah, I think that answers the question, and thank you very much for answering the question. Let me just have a one last look at the YouTube chat. So yeah, so I have a question which goes something like, this is philosophically and sounds ideal. Humans should have an okay, so it's not a question, it's a statement. I'm sorry, I didn't read it. So yeah, I think let me just have a last look. Yeah, I think like we're done with the questions from the YouTube chat. So
I see that there is one question. I think some like how can we? I'm looking at the YouTube chat. What is the best resource to get started?
oh yeah, sorry, I'm sorry, I
Yeah,
just missed that. Yeah,
yeah.
sorry.
I think I think Peter Abil, like at least if you're talking about reinforcement learning and robotics, Peter Abil has a very good course, a very short crash course, and lectures are probably online. You can start from there, and I think in that course he tells other resources as well, so you can probably follow that. But starting from a course is probably a good idea, and then trying to implement papers, whichever paper you like, try to implement it. And in fact, these days, most of the papers release code, and so you can try to implement it on your own without looking at their code and see the code for more help. And there is no other way to learn faster than this approach.
Yeah, all right. So I think Chetan has a question for you, Deepak. So I think I would let him ask him. I'll ask you.
Yeah.
Yeah, hey Deepak. So in the am I audible?
Yeah, you're audible.
Okay, so my question was related to your Mario game that you showed. So there was a bar in the bottom right that showed the distance percentage that we are covering. So I wanted to ask, like, if that is a goal that we are setting for Mario to complete, or if that is the case, wouldn't it be something out of curiosity and more of a task-based thing?
Oh, I don't think we are setting that goal actually. We are not using that as a goal. It may be in the video, but well, I'm not sure there's a bar, but you are, oh, I see. So there is this distance, I think. Okay. I didn't notice this. Well, I expect that the RL agent is not that smart to read the text from the image and use that as a signal. If probably it's doing that, I'm probably underselling. uh,
Okay,
so,
okay.
I don't think that part is useful. Anyway, this image get resized to a very small cursor resolution, so it's probably not visible that clearly. And this number resets also. So we are not using that as an objective function. So what I mean by objective function, like usually in RL, what you do is you take that number from the RAM of the game and then you pass it as a reward. We are not doing any of that. So it only looks at the image. I noticed it for the first time, and now that you said it, there is a distance. And nobody has noticed it before. But yeah,
Okay,
it's probably
that
not,
makes
it's
sense.
not something that I can show that part.
Got it. Thank you.
Yeah. If it's using that, it's like super smart tech. We should already go home.
Yeah, all right. So I think we should end the Q&A section for now. And I have like a couple of, I'm just going to take like 2 minutes of the time of the audience to just tell a few things. So there must be a link to a small feedback form on your screens right now in the bottom. And you can go to that link and just let us know how was this online meetup, and if you have any recommendations for the or any anything that you want us to get speakers on for the next meetup, and we'll definitely look into that. And I see there was a question in the chat which says something like, how do I submit my proposal to the PyData Global conference? So please go to global.pydata.org and you will find all the relevant links over there for the CFP, for the questions related to CFP and how to form a proposal if you're a first time speaker. And there's a mentorship program for speakers, if you want to get tips from the experienced speakers. We basically pair you up with the experienced speaker and he'll help you through the proposal and everything. So yeah, that's that. And I think so is the feedback form live on the YouTube? May I know, because I don't see. Can anyone confirm?
No, it's not yet there.
Okay, I see it now. So, yep, I think that's it for the meetup for today. And thank you very much thank you everyone for joining, and especially thanks to speakers Hariram and Deepak. Thank you very much for coming, and it was awesome. It was great pleasure to have you, both of you, and talks were amazing. We got interesting questions, and the team was so into both of the talks. We learned a lot of things, industry wise and academia wise, and how to get started in a few in interesting fields. Like myself, it was very new experience for me. So yeah, and I think we can stop the live.